Hello, in this video I'm going to run through a few questions on nuclear physics, particle physics, radioactivity. They're all grouped together. So we'll see how we get on with these. State with a reason whether or not protons and neutrons are fundamental particles. So first of all, stating no, they're not, because they're made of quarks. And fundamental particles, nearly said quarticles, fundamental particles cannot be made up of other particles. That's why they're fundamental. Right, so that's A. B, state two fundamental particles that can be classified as leptons. So remember, leptons are the other fermions alongside quarks. So we're looking at the electron neutrino with antiparticles, and then you've got the generation 2 and generation 3 ones. So the muon neutrino, and tau neutrino with antiparticles. So let's just go with the generation 1 options. Now in C, some fruits such as bananas are naturally radioactive because they contain the unstable isotope potassium-40, which is a beta minus emitter. Complete the following decay equation. Right, so if it's beta minus, we need to have an electron, we need to have our anti-neutrino, which is going to be an anti-electron neutrino because it's an electron that's come out. Now we need to get our numbers to add up. We're not getting any nucleon number for the electron, so we must have 40 still for the calcium to make them add up, and we get -1 charge, so we must have 20 for the calcium, so we got 19 is 20 minus 1. Explain why energy is released when a single nucleus of potassium-40 decays. Right, this is going to be to do with the binding energy. So this electron has come from the nucleus. This has been created from energy in an interaction that's gone on in the nucleus. This is the weak interaction. The weak interaction has taken some of that energy, the binding energy of the nucleus, and chucked it out in the form of the electron, which of course has got mass and energy of itself, of its own. So it's all to do with binding energy here. I mean, this is where the mass and the energy is all kicking around inside the nucleus of an atom. It's all this, this gluon action that's going on, that's holding the quarks together and then holding the nucleons together. So the binding energy per nucleon is higher in the calcium, than in the potassium. I should really put the 40s after each one of these. So calcium 40 than in potassium 40, and it's because they're more tightly bound that this decay is taking place. I mean, you're getting a more stable result on the right hand side. This calcium nucleus is more stable. The nucleons are more tightly bound together, and that's the driver behind why this beta decay is happening. So don't get confused about the binding energy. Remember that a higher binding energy means that you need more energy to separate all the nucleons. That's what binding energy is. It's the amount of energy you need to separate the nucleons. So more binding energy actually means there's less energy inside the nucleon. So it's got a lower mass. It's a little bit counterintuitive, but that's what the definition is of binding energy. All right, looks like we're ending on a calculation. So we've got a banana containing 4.5 times 10 to the minus 4 kilograms of potassium. A small amount of that mass of potassium is unstable. And it's got this half-life, and it's got that molar mass. Right, so they've given us a lot of information here. Now we need to calculate the activity. So remember that activity, radioactive activity, is associated with a particular sample. It is a number of decays per second that we're actually getting from a particular sample, and that is the number of atoms multiplied by the decay constant. Because remember, the decay constant, which is equal to natural log of 2 divided by the half-life, that is the probability. So that is the probability of decay per second, and that is for a particular substance, not an amount of substance. So if we take the probability of decay per second and multiply by the number of atoms, then we're going to get the number of decays per second, which is the activity. So we know what the decay constant is because they've given us the half-life. So we need to get now the number of atoms that could potentially be decaying. So the number of atoms, this is going to be we need first of all the number of moles we've got. So the number of moles is going to be our mass, 4.5 times 10 to the minus 4, divided by our molar mass. And if you're ever wondering about, oh, that's just 0.04, I don't need any tens on those. So that's going to be the number of moles. And you can see that from the units. So if we got kilograms and kilograms per mole, and we want to end up with moles, well, we have to divide that by that. That's the only way that gives us moles. So we've got that. Then we need to multiply by Avogadro's constant, 6.02 times 10 to the 23, all in the formula booklet. And then we've got this tiny percentage as well. So we need to multiply by 0.012 divided by 100. So we've got to multiply all that together, and then we need to multiply it by log 2 divided by 4.2 times 10 to the 16. So all of this stuff is multiplied together. Right, let's try getting rid of some of these powers of 10. So we've got there 16, 20, 22, which gets rid of all of that. We've then got, we can get rid of those two zeros with those two zeros and make it a 1.2. We'll multiply that 1.2 by the 10 to make it a 12. Divide it by the 4 to make a 3. So we're ended up with 3 times 4.5 times 6.02 times log 2 divided by 4.2. So let's type all of that into the calculator and see what we end up with. So 3 times 4.5 times 6.02 times natural log of 2 divided by 4.2 is 13.4. 13.4. Are we okay at three significant figures? We aren't usually. No, we've got 2 there, 2 there. Okay, they've given us 3. Oh no, 2 there. 2, well, we've got 2's everywhere. So let's go 13. And this is decays per second. So becquerels. So yeah, quite a nice question covering a lot of ground there. So yeah, make sure you understand this with binding energy. That's quite a, well, it's a very key idea in all of this. And then this idea of activity being a real world, this is what we're getting if we're actually counting decays per second for a particular sample versus the decay constant and the half-life, which are just to do with the material, not the amount of it. Nice. All right, next up, we've got to explain how the experiments on the scattering of alpha particles by a metal foil provided evidence for the nuclear model of the atom. Okay, right, there's a few things we want to say about that. So we need to say that, oh, on the wrong sheet. So we need to say that, so most alpha particles pass straight through. Pass straight through. So that's first of all. And then we've got that some experienced large deflections. Experienced large deflections. So you don't want to say reflections because it's not, there's no reflection happening. It's either a scatter or a deflection or something like that. But you make sure you don't use the word reflection. You know, this isn't light bouncing off glass or something like that. This is a different thing. So we've got these two things that they saw. You know, we've got most of them have gone straight through. The vast majority of them have gone straight through. And then every now and again, you get one of them that would do something crazy like that. So what did these two things mean? So off of the basis of the first one, we've got that most of atom is empty space. Obviously, you'll put these into slightly more coherent sentences. And then off of the second one, there is a small concentration of positive charge. So these things are linked together. So yeah, we're saying, how did they behave? These are the observations, these two first bits. These were the two things that they saw. And then what does that mean? Empty space, concentration of positive charge. Right, figure 5.1 shows an alpha particle, this kinetic energy, moving directly towards the nucleus of an aluminium atom. Initially at rest, the alpha particle comes to rest instantaneously a short distance away from the aluminium nucleus. It then reverses its direction of travel. Okay, so it comes in, goes out. Okay, so it's one of these crazy cases that we saw in the second observation. Describe and explain the motion of the aluminium nucleus at the instant the alpha particle is at rest. Right, well, it must be moving away. Yeah, we've got a change of momentum going on for the alpha particle. We must have the same change in momentum of the aluminium nucleus. So that can be our explanation as well. So due to conservation of momentum, the aluminium nucleus moves to the right. Moves to right. So that's fine. Calculate the initial speed of the alpha particle. So this is just making sure you know what this 8 mega electron volts actually means. So our energy, which is the half mv squared that we're looking at here. So we've got half mass of the alpha particle is that 6.6 times 10 to the minus 27 times v squared is equal to 8 times 10 to the 6 times 1.6 times 10 to the minus 19. So we just need to solve all of this for V. So V is going to be equal to, what are all of our numbers here? We've got 16 multiplied by 1.6. So let's just make that 25.6 then. So that's dealt with the half, the 8, the 1.6. Divide that by 6.6. And then we've got 10 to the minus 19. That'll make it 10 to the minus 13. So that'll be times 10 to the 14. And we need to square root that. Is going to be our V. So that is 25.6 divided by 6.6 is that square root that gives us 1.97, and that'll be multiplied by 10 to the 7. So 1.97, we'll have to go for 2 then. 2.0 times 10 to the 7 meters per second. The electric force experienced by the alpha particle when it is close to the aluminium nucleus is 270 newtons. Calculate the separation. Okay, right, this is something I haven't actually covered in my videos yet, but I'm sure a lot of you would have already looked at the force between two charged particles, which is the charges multiplied together divided by 4 pi epsilon 0 r squared. So we've got the charge on the alpha particle is 2 times E, and the aluminium nucleus has got, there we go, 13. So we've got 26 E divided by 4 pi epsilon 0. What was epsilon 0? Got to look that up. It's 8.85 times 10 to the minus 12. And then multiplied by r squared. So, well, let's flip these around and say that if we multiply that by 270, that would be equal to r squared. That E, of course, is 1.6 times 10 to the minus 19. Oh, of course, it'd be E squared because we've got E for both of them. So that will have to be squared. So, yeah, at least that's coming out a pleasingly small number. Because that's what we want out of all of this. So let's try typing all this in. 26 times 2.56 divided by 4 is that, divided by pi, divided by 8.85, divided by 270. Right, so we've got that, that's fairly small. And then we've got 3826 times 10 to the minus 26. 10 to the minus 26, and that's a 5, that's a 6. And then square root, which is giving 4.71 times 10 to the minus 15. So 4.7 times 10 to the minus 15 meters. So, yep, nice and small. Now we're on to part 5. Consider the situation where the alpha particle travels much closer to the aluminium nucleus than in the last part. Discuss how the strong nuclear force may affect the resultant force on the alpha particle. Right, so yeah, the strong nuclear force, I mean, this is something that becomes attractive at very short distances, around about 10 to the minus 15 meters. So yeah, if we get close enough, I mean, even 2 times 10 to the minus 15 is going to start kicking in. So, because remember, we've got that, it's an attractive force, but it's only really operating, over this short range here, where you're looking, it's peaking there at about 10 to the minus 15, the attractive force. That's when the strong nuclear force is at its greatest effect. So this is attractive at sort of, around about, I don't know, 0.5 to 2 times 10 to the minus 15 meters. So the resultant force will be, well, yeah, it will start to decrease because the strong nuclear force will get, more and more influential. So the resultant force will decrease until at some point it will become 0, where the electromagnetic repulsion is exactly the same as the attraction from the strong nuclear force. And then the resultant force will go off to the, attracting the two particles together. So that's what we've got. It depends how much of a discussion you actually want here, but you could go through those stages. So you can say initially we've got the resultant forces to the left. This will then decrease as the magnitude will decrease as the strong force increases. Then you can say it will reach some kind of equilibrium, and then it will go off to the right when we get inside this, maybe half this distance or a little bit less than that. So yeah, it's just bringing in this force rather than saying, well, we've always got this force that's pushing them apart. Eventually we're going to get this force that's pulling them together with the strong force, and of course that's what's binding these atomic nuclei together.